Hello folks, today we're going to look at 7-3, day 2, and we're going to take a look at the second part of this one here. So we're going to look at this part of it today, write and evaluate, and then we're going to graph logarithmic functions. So that's where we're headed for today, so let's get started. Here is a warm-up question. Go ahead and do these 3 questions, and then we'll get back and look at them here in just a few minutes. Pause the video, please. Okay, so for this first one here, it says 4 to the 4th power. You have to remember something here on this one here. And what you're going to remember here is that that is the same as the 4th root of 16. So what times what is 16? Well, if you take 16, break it down, goes in there 2 and 8, breaks it down, 2 and 4, breaks it down, 2 and 2. So you have this is the same as the 4th root of 2 to the 4th power, which is, yep, you said it, it's going to be 2. Okay, let's take a look at our second one here. The second one here, first of all, I want you to notice that it has a -3 right there. Because it has a -3, we need to invert this. And then, of course, you're just going to cube everything. So you're going to flip it over. The inverse of 2/3 is 3/2, and then you're going to cube it. So your answer will be 27 over 8. All right, let's move on. In question number 5 here, it says a power has a base of -2. You're raising it to the 4th power. So that means it's going to be -2 raised to the 4th, or 16. Okay, let's get started with today's material. We are going to take a second right now and we're going to review. Okay, remember the 3 words that you wrote down in your notes last time. Logarithm, common log. Now remember, a common log had a base of, you said it, 10. And then a logarithmic function, and that's the new one we're going to take a look at for today. So let's go ahead and review just a little bit more. In this slide is an example of a problem that we did last time, along with the definition of a logarithm. Okay, and that's what you see right here. Now, here is a problem right here. Now, I'm going to explain this problem, and you're going to have this problem done, and you're going to give it to me on the way in the door to class tomorrow. Now, here's the problem. Now, here's the scenario. Would you rather somebody give you $1,000, or would you rather be given 1 cent, and that amount doubled each day for 30 days? In other words, the first day you're given a penny. The second day you're given double that, 2 pennies. The third day you're given double the 2 pennies, 4 pennies. The fourth day you're given the double of that, which is 8 pennies. Now notice, you're getting 8 pennies given to you plus what you originally had. Okay, so that's the task. Figure out which would you be rather given and hand that on a sheet of paper coming into class tomorrow. Let's review how to convert an exponential equation to a logarithmic equation. And here is the rule for doing that. So now remember here, the base of the exponent becomes the base of the log. The logarithm becomes the a value right there, and the exponent becomes what is equal to. In other words, the inside-outside switch places. So let's go ahead, pause the video, and I want you to convert this problem for me. Okay, now that you have that converted, let's go ahead and do it. So, first of all, we have the log. The base of the exponent, which is right there, becomes the base of the log, and the inside-outside switch places. So this, what the log is equal, that is the log, okay, 81, and that is equal to 4, just like that. To start out with new material today, we're going to define what a logarithmic function is. So in your Cornell notes, write down logarithmic function on the left side, and on the right side it is the inverse of an exponential function. In this slide, we're going to define what a logarithmic function is. Now, a logarithmic function is a function, it is the inverse of an exponential function. So here's an example of an exponential function. If I convert it using that previous property I just showed you on the previous slide, it converts to this. That is the logarithmic function. Now, something I want you to notice here. If we take a look at, and let me uncover this, if we take a look first of all at the exponential function, it is going to be here in blue right there. Now, if I were to graph the logarithmic function, it's going to look like this here. It's going to look like what you see in red. So notice it's a reflection. Each of the points of the exponential function is a reflection over the line y equals x. All right, so now notice your domain for the exponential function is all reals, and your range is from 0 to infinity. Okay, to find the domain and range of the logarithmic function, it's going to be the reverse of that. And I want you to get this down into your notes. So, looking here in, notice right here, your domain is going to start right here at 0 and go to infinity. And of course, its range is going to be from negative infinity to positive infinity. So, the domain of the logarithmic function is going to be everything greater than a 0. And the range is going to be the set of all reals. So let's go ahead and graph one here. So we have a function here, f of x equals 1.25 raised to the x, and you're going to substitute negative 2 in for x. So take your calculator and do that, and I want you to deposit, and then when we're done, we're going to uncover what these are here, and you'll be able to see, and then I want you to graph it, and we're going to see what it looks like. All right, so let's go ahead and do this. So first of all, for negative 2, you should have gotten 0.64. For negative 1, you should have gotten 0.8. For 0, you should have gotten 1. And for 1, you should have gotten 1.25. And for 2, you should have gotten 1.5625. When you graph each of these, notice it's going to look like a graph just like this. Okay, so that's the exponential function. So let's look at what the log of this is going to be. In other words, what is it going to look like if you found the inverse of this? To find the inverse of this, first thing you're going to do is you're going to swap your x and y's, and then you're going to solve it for y, and you're going to come up with this equation right here. All right, so we have log base 1.25 of x equals f inverse of x. Now, what's going to happen to the domain and range? Yes, you're right. They are going to switch places. So what on the previous slide was a domain now becomes a range. And what on the previous slide was a range now becomes a domain. All right, so let's get this out of the way. So now we're going to graph it. And notice when we graph it, here's the graph of the domain and range. Now notice here what I want you to see here. Notice the logarithm is a reflection over the line y equals x. All right, now, so tell me about the domain and range overall. Okay, well, first of all, the domain for the exponential function right here was all reals. So it becomes the range of the logarithmic function. And the range of the exponential function, remember, was from here up, so it was anything greater than a 0. So that becomes the domain of my logarithmic function. All right, so let me uncover, and that is the way that works out. Okay, so get this down in your notes, please. For this function, you're going to see something a little bit different. Notice the last one had a base of 1.25. That was greater than 1, so it increased. Notice here, it is between 0 and 1. It's 1/2. That means this function is going to decrease. Okay, so if I plug in negative 2, negative 1, and so forth into there, this is what it's going to give me. So I'll just uncover this. It's going to give me that right there. Now, so we graph that, and that gives us this function right here. So now we're going to find the inverse of that. To find the inverse of that, remember what we have. We had y equals 1/2 to the x power. Okay, so I'm going to interchange the x and y. So that gives me x is equal to 1/2 to the y. Then I'm going to use definition of a log to solve for y. So that gives me y is equal to the log of 1/2. Notice the base of the exponent becomes the base of the log, and then the inside-outside switch places. So it's going to be log base 1/2 of x. Okay, so now we're going to take this function, and we are going to graph it. But I want you to notice something here. Because of this right here, we cannot enter and find the values of that. I can't even graph it. With the current knowledge that you have, we can't graph it. So what are we going to do? Well, guys, we are going to use the reflection over the line y equals x of the exponential function to find the graph of the logarithmic function. Okay, so let's go do it. Okay, so let's start with what we have here. First of all, we know here's our function, so let's get rid of that. And let's go a step forward more here, and we're going to put a little 1/2 there. And I want to know, where is it for 4? What do we do? Well, we can't do that, okay? As I said, we can't do that because we can only handle, at this point, the common log. Okay, so since I can't do that with my current knowledge, let me go ahead and we're going to graph it. So here, let me show you here. So, for starters, all right, let me remove this. Okay, and here's what we have. Okay, I have the exponential function looking just like this. So I have the line y equals x running right through there like that, and I flip it over there, which means it's going to be this. So this is the graph of my logarithmic function. So where is that graph at 4? Well, we look at 4, and it looks like it's going to be right there. Now, we know it's asymptotic to the x-axis, so that value is going to be, and let me just uncover these here, and we'll show it here. Okay, so here are the values, -2, -1, so on and so forth. Now, I want you to see this here. If you were to take a look at the exponential function, we find each of those values just by flipping or interchanging the domain and the range. Okay, so there it is. So that tells me here that the domain is going to be, and let's get rid of this, all values greater than a 0, and your range value is going to be, as you know, all reals. In this slide, let's review the log button. When you hit the log function on your calculator, whether it's your device or your graphing calculator or just your plain old calculator, if it has a log button, you're finding log to the base of 10. Okay, so that's all I want to clarify here. Okay, so on this slide here, it says the table shows the hydrogen ion concentration for a number of food items. Find the pH of each of these. Okay, so in finding each of these, we're going to take each of these numbers that you see here and we're going to plug them into the formula on the next slides. So I want you to pull out your calculator and do that. Here's the formula that you're going to do. You're going to hit negative, then you're going to hit the log, and then you're going to type in that number. So in this case, it's negative log, and you're going to punch in this value right here, and then hit enter. Now this is the way it's going to look as you punch it into your calculator. And when you do so, your answer should look like that. Okay, so that means the pH value of milk is going to be this value right here. Okay, now you go do it for the next two. Okay, here's this slide here. All right, punch it into your calculator and pause it and tell me what you get. All right, here is what you get. You're going to get 4.5, so the pH of tomatoes is 4.5. Now go ahead and plug in the value for lemon and tell me what you think the pH value of lemon juice is going to be. Okay, folks, that's going to wrap it up for today. Please write this down. This is going to be our problem set that we're going to work on next class period. All right, and don't forget, you have an entrance quiz as you come in the door next class period. So make sure you have that problem worked out and you're ready to hand it to me walking in the door. Have a good day, and I'll see you tomorrow.